Talking about some computational techniques for Hecke operators, especially for SL, and talking about some results also. Most of what I'm doing here today is joint work with Avner, Ash, and with Paul Gunnells. Gunnells, Danyasaki, and I have also worked on some similar things recently. Another thing I'll be doing today is announcing a new algorithm that Bob MacPherson and I have been working on for computing Hecke operators for SLN in a wider range of degrees than possible previously. Okay. Well, let's always start with some background. So a boldface G will be a connected semi-simple algebraic group defined over Q. Then ordinary G is the real points of the group. We choose a maximal compact subgroup K. So X is G mod K is the symmetric space. And I'll be taking gamma to be an arithmetic subgroup of G. So the main example today will be, the group is SLNR, of course, K, the SO is the maximal compact, and gamma is a congruent subgroup. But from time to time, I'll also be addressing the question where G is the restriction of scalars of GLN over a number field with ring of integers O of K. Yeah, I just said semi-simple. GLN is reductive. The units of O of K can get in there and make you think a little harder, but that's okay. As you probably know, if you're looking at real quadratic fields K, this leads to Hilbert modular forms. The imaginary quadratic case leads to Bianchi groups. So the G I've mentioned so far are going to have their symmetric space X contractible, and gamma will act properly discontinuously on X. So if gamma is torsion free, then X mod gamma is going to be a K pi 1. So the group cohomology of gamma is going to be the same as the cohomology of the manifold, the locally symmetric space X mod gamma, for the moment with complex coefficients. But we don't always only want complex coefficients. So we want general coefficients. So M will be a rational finite dimensional representation of G over some field F. Usually the field will either be the complex numbers or later on it'll be the field of P elements. So this gives a representation of gamma, and hence gives you, as we've seen in several other talks today, a local system, script M, on the locally symmetric space. Then the cohomology of the group with coefficients in M is the coefficients, is the cohomology of that local system. Then if gamma has torsion, well, that last equation is still true if the characteristic of the field does not divide the order of any of the torsion elements. And in fact, I don't really need to say that, because even if the characteristic of F does divide the order of some torsion elements, I'll have a few things to say about that later. Okay. Then a major result in this area is that the cohomology of gamma breaks up as a direct sum of the cohomology called the cuspidal cohomology, which is supported on the open part of the symmetric space itself, and then parts which we can think of as coming from the Borel-Serre boundary, the cohomology for the associated proper Q parabolic subgroups. So basically the parabolic mod gamma, and you compress down to the Levy factors we've seen before today. So you take the cohomology of all those compressed pieces. You think of these as being from the boundary of the Borel-Serre compactification. Excuse me?
So how do you define cuspidal? So your coefficient system is a rational vector space.
Mm-hmm. Mm-hmm.
So your cohomology groups are rational vector spaces.
Mm-hmm. Yeah.
So what is cuspidal?
That's right. So this is, I'm taking this by taking all of Franke's work on automorphic forms, and then we're restricting it to the, so we're talking about cuspidal automorphic forms, and then bringing that down to cohomology.
If you do this in a very general context, cuspidal cohomology is not clear whether this is defined over Q.
Okay.
So cuspidal is not, but just go ahead, yeah?
Yeah, yeah.
It doesn't play such a role, but what is
Okay, right, yeah. And I would say, well, it's the cohomology supported on the interior, but then, of course, then I get into questions of Gauss classes, and no, yeah, I know it's not that. That's right. Well, yes, you're right. I should just, I'll have to leave that question at this point. I say projects we've done, what I should have said is, rough outline of the talk to come is, we do computations where we try to identify all these terms explicitly. We're looking for cohomology that could be supported on cuspidal automorphic forms in the center of the thing. We're also trying to identify the other pieces. We do this by computing the Hecke operators on the whole thing. This helps us sort out which piece is which on the right-hand side. It also leads us to identify conjecturally Galois representations that are attached to the various pieces here. I'll be saying more later what it means for a Galois representation to be attached to a cohomology class. We've done this for both non-torsion and torsion classes in a series of papers, in different papers. All right, so let me back up a bit so I can give you some of the geometric ideas that underlie this. So for this slide, let's just talk about SLN. In fact, in this slide, just SLNR. So to set up a little formalism, SLNR is an n by n matrix, determinant 1. So its rows are a basis of Rn, of determinant 1. So I'm going to call a G, the group is really the set of bases of determinant 1. When SLNZ acts on the left, it forms a linear combination of those rows. Given a basis, the basis spans a lattice. SLNZ acting on the left is going to form new bases, but of the same lattice. In this sense, we can say that G mod SLNZ is the space of lattices in Rn, determinant 1. Take a congruent subgroup gamma, you could interpret that as a space of lattices with extra structure, like level n structure. I won't go into that. Then we made a choice of maximal compact subgroup K earlier. Usually you just take the standard dot product on Rn, so you get the standard SONR. So that puts an inner product on the lattice, which I suppose it didn't have before on this slide. So then in this formalism, X G mod K is the space of lattice bases modular rotations and reflections. And so finally, X mod gamma is a space of lattices with extra structure modular rotations. So basically, when I talk about X mod gamma, think of a point in that as being a lattice, and rotations don't matter. Okay, so this leads to the definition of arithmetic minimum, which you've already seen. The arithmetic minimum is the minimum of all the lengths of the vectors in the lattice, not counting the zero vector. And the minimal vectors of the lattice are all vectors that attain that minimum. And as an important definition here, I'm going to say that a lattice is well-rounded if its minimal vectors span Rn. Basically, if the lattice is nicely enough shaped that it has enough minimal vectors to span Rn, like have at least n linearly independent directions. Now, we just heard a talk on perfect forms. To compare those two notions, a lattice is perfect if it's got so many minimal vectors that just specifying what its minimal vectors are specifies the geometry of the entire thing up to homothetian reflection. So well-rounded is a much weaker condition. Like for well-rounded lattices in 3 space, for instance, think of 3 vectors of length 1, and that the lattice they generate maybe doesn't have any other vectors of length less than 1 in it. And so you can see there's plenty of wiggle room to move those angles around by small amounts. And if it's really small, then the lattice will still only have those 3 minimal vectors. Okay. Well, let W in X be the space of bases of well-rounded lattices. I'm going to illustrate that, show you what that looks like in the next slide. But so this set of ideas, several people had worked on it, and a theorem due to Avner Ash putting together a series of ideas, say in the late 70s by the time it was finally formulated. The theorem goes as follows. First, there's an SLNZ equivariant deformation retraction from the space of all lattices to the space of well-rounded lattices. So that the well-rounded lattices, this space is called the well-rounded retract. So, okay, it's fun to describe how this deformation retraction goes. So imagine you're given like an arbitrary lattice. I say determinant 1, but I can rescale up to homothetes, so let's rescale so that the arithmetic minimum is 1. So the shortest vector has length 1. If it's a generic lattice, there's only 2 shortest vectors, like x, and it's negative. So that shortest vector determines a line. Now, the basic operation is fix that line and also fix its orthocomplement of dimension n-1. And we're going to shrink in the n-1 dimensions of that hyperplane, shrink down uniformly, like zoom in, while not shrinking in the dimension along the line. So as you shrink in, it's like a tin can contracting, eventually some second vector is going to come in here and fall on the sphere of radius 1, bump. I've got a second minimal vector now. So now that if you have 2 independent minimal vectors, fix the plane through them, shrink in the orthocomplement n-2 dimensions, eventually some third vector will fall on the minimal sphere of radius 1. Now you got 3. And you do this, so at most n-1 steps will get you down to well-rounded. If you ever have ties, don't worry about it. Just it doesn't have to be dimensions 1, 2, 3 in order you can get a partial flag going. But so it's a continuous retraction. So that argument pretty well proves that the dimension of W is n-1 less than x, and one knows that this is the virtual cohomological dimension. Virtual cohomological dimension means the top dimension of x that can actually carry cohomology, of neglecting torsion effects. Furthermore, again, I'll show pictures in a moment, but this well-rounded retract is a locally finite regular cell complex. The formal way to say it is the cells are characterized by the lattice has got a basis of minimal vectors, and you look at coordinates in Zn of the minimal vectors with respect to I misspoke there. The elements of W just are some lattice basis that's well-rounded. The minimal vectors may be somewhere else, but the coordinates of the given basis lie in Zn with respect to the minimal vectors, and the cell is the locus where those coordinates are constant as you vary the thing under small perturbations. Yeah. Oh, yeah. Thank you. I can just do my hand, right? Yeah. Good. Yeah. Okay. Something certainly to say to this audience is that something very much on Ash's mind was that this whole construction is dual to Voronoi original construction, his 1908 decomposition of X into polyhedral cones, which is done precisely by perfect forms. Indeed, the vertices of the well-rounded retract W are the perfect forms. So there's a duality, as I say. It follows from a number of things here that W mod gamma would then be a finite cell complex. Okay, so for SL, well, one more slide. I've described it over Q, but Ash, in fact, did this for SLN or GLN over a number field, not just over Q, in a later paper. So the conclusion is that I've got a finite cell complex W mod gamma. That's something with which I can compute cohomology in finite terms. There's a lot of questions about how do you do this efficiently in time and memory and tweaks here and there. I put those in Appendix 1, which is like later in the set of slides. I'll also be speaking in the Thursday session on software, and I think I'll show you some of Appendix 1 on Thursday, so skip that for now. Right, so the well-rounded retract is well known to everybody as the tree in the upper half plane. So when n equals 2, and we're working over the number field Q, then X is just the upper half plane, and the shaded region, both sides, is a fundamental domain for SL2Z, but you're all familiar with how the domains go here and here, and then the lines like this lie between the domains. So this graph is the well-rounded retract W in this case. So it's a graph. It's made of edges and vertices. Each edge, of course, is on 2 vertices, but it's a trivalent graph. Each vertex is on 3 edges in W. So the vertices are the perfect forms. They're the hexagonal lattices. The edge centers are coming from square lattices. The well-rounded retraction itself is like above the graph at the top, just flow straight down vertically. Well, that's better known as the geodesic action. And down here, what you do is you also flow along geodesic. You know, geodesics in the hyperbolic plane are circles that are perpendicular at the two edges down here. And so you flow along circles going up vertically and then following the circle, flow to here, flow to here, flow to here. So, for n equals 3, well, for n equals 2, it was a graph with things stuck together. For n equals 3, it's Soulé cubes stuck together. So W is a contractible three-dimensional cell complex, and all the top dimensional three cells are combinatorially the same, and they're Soulé cubes, because, well, it says down here, when k equals q, this complex was first constructed by Soulé and Lahn in various things. I first learned of it from Soulé's thesis, the published version. And I could kick myself. I now have learned how to do Soulé cubes on a 3D printer, and I was going to bring my Soulé cube and show it to you, but you'll have to do with this old picture. So, like I said, for SL2, you take a graph, and there are 3 edges at each vertex. So here you take this truncated cube, and at each hexagonal face, you glue together 3 of the Soulé cubes. Of course, they don't overlap when you're in the 4th, 5th dimension. And you're in the 5th dimension, dim x equals 5. At each triangle, you glue 4 of the cubes together at a common triangular face. The vertices, like I say, are perfect forms. In dimension 3, there's only one perfect form, which is A3, the A3 lattice, which is also the D3 lattice, which is how the oranges lie at the supermarket, if you're very careful how to get the planes all arranged in a lattice order. Okay. Excuse me. It's a good time to mention that Ash and I proved back in '96 that, in fact, for all SLNs, and including over number fields, the well-rounded retraction extends to a retraction from the whole Borel-Serre compactification down to W. It's, once again, we proved that it's a composition of geodesic flows away from the boundary components. You have to do a little extra work to get going when you're out at infinity, and then just keep flowing in the rest of the way. Question?
Your cell complex W is only 3-dimensional.
Mm-hmm.
How can you glue more than 2 3 cells together at one triangle?
Well, if you were in the 5th dimension, you could do it easily and they wouldn't overlap. But it's the same as in a graph, you know, the cells are only 1-dimensional. How can you glue 3 to a vertex? Well, just go into a 2nd dimension and yeah. That's right. Yeah, that's right. Other questions? All right, let's see. All right, so talking about, let's introduce Hecke correspondences, or Hecke operators. So throughout the talk, L will be the prime where I'm doing the Hecke operator at L. And let K be an index in 1 through n. Let gamma equal SLNZ for most of this when I discuss Hecke operators for the sake of simplicity. So then X mod gamma is just a space of lattices. Okay, so here's the way to think of it. Given a lattice L of rank n, there's only finitely many sublattices M in L, where L mod M is isomorphic to a Z mod LZ to the K. There's only finitely many directions in which you can go in L, like give yourself index little l in k different directions. There's only finitely many ways to do it and still build a lattice. And so the simplest definition of a Hecke correspondence is, remember, a correspondence is a one-to-many map. A correspondence is a function that sends one point to many. So the Hecke correspondence is the one-to-many map from the space of lattices to itself that sends a given lattice to all of these sublattices M. So I've been teaching a course on this to, well, I've been teaching a course to some undergraduates recently on, we do sort of basic modular forms and then touch on this SL3 and SL4 stuff a little at the end. But for the students, I made this picture of Hecke operators for SL2. So, okay, on the top row here, I've got the 3 sublattices of index 2. I fix a lattice, it happens to be the square lattice. So there are 3 ways to take a sublattice of index 2, like horizontal rows, vertical rows, and the checkerboard. Okay. There's 4 ways to take a sublattice of index 3, horizontal, vertical, and 2 different of slopes. Okay, of course, it's p plus 1 in general, and it has to do with the projective line. But the nice thing is that you intersect these possibilities, and you get the 12 different sublattices for a working modulo 6. So the Hecke operator T61 sends L to the 12 different m's you see here in the body of the table. Okay. Well, for the purposes of computation and writing down clean formulas, people usually write it in another way as follows. Let's fix, again, the prime L, and I'll be talking about the Hecke operator at L. Let T be the diagonal matrix with, 1, 1, 1, L, 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 so with k copies of the L. I also need the congruent subgroup gamma naught. So, the standard gamma naught of n is things with, at the bottom, it's congruent modulo n to a single row of 0, 0, 0, 0, 0 star. I need that here for k. I need matrices in SLNZ congruent to star, star, 0 star mod n, where the upper block is n minus k by n minus k, and the lower block is k by k. Okay. Now, a standard way of defining Hecke operators is you have 2, well, you consider x mod gamma, and you also above it consider x mod the intersection gamma intersect the gamma naught of LK. You have to worry about whether gamma itself might have a level divisible by L or not, but this definition should work in either case. So I've got these 2 spaces, and I have 2 maps between them. The first map is simply map the coset of G down to the coset of G. The second map is map the coset of G down to the coset of TG for this T. And it's a nice exercise to show that it's actually, the S is actually well defined. Pick a point downstairs, pull it up by R, you get multiple points given by the numbers given by the index. Then push those multiple points back down by S, and generically, they'll all go to distinct places. So that's why it's a one-to-many map. So the Hecke correspondence, TLK, is defined to be do S after R inverse. Then on cohomology, everything dualizes, so it's R lower star, a push down after S upper star. So now you do this for all primes L and all K, and they generate a commutative algebra. It's commutative because of the picture of lattices I showed you, called the Hecke algebra. Okay. And that algebra then acts on cohomology, and that's called the algebra of Hecke operators. Okay, but the main question for this talk would be, how do you compute Hecke operators using these cell complexes? So here, let me illustrate the difficulty. So I showed you the pictures of the 3 sublattices of index 2 for SL2, horizontal, vertical, and checkerboard. If you translate that to the usual upper half-plane picture with Mobius transformations, what you're doing is multiplying by 3 matrices 2, 0, 0, 1, 1, 0, 0, 2, and 1, 1, 0, 2. So you got 3 matrices. You've got to take this whole tree here. For each of those operators, multiply it by the matrix and see where it goes. So you'll have 3 distinct trees, like overlapping and crossing each other. But you can already see from the first operator, 2, 0, 0, 1, that there's going to be trouble, cellularly speaking, because 2, 0, 0, 1 is the Mobius transformation, merely z goes to 2z. So take a point in the upper half plane multiplied by 2. Well, if you do that, 0 stays at 0, and everything else stretches twice as big, like along radii of circles. So z goes to 2z is going to take this, so arc in the center, it's going to send it twice as far out, so it starts now hanging over the midpoint here, twice as far out, take it to a bigger circular arc lying over here. So, okay, well, a big circular arc. I said that the retraction, well, first of all, you just carried your cell out of your cell complex. So that's bad. Then you say, well, I'll just retract it back. I have the nice retraction. which is to push straight down by geodesic flow. But now that what you push it down, you've got half of this cell plus a whole of this cell plus half of this cell. So you've got a bunch of half cells there. And well, okay, maybe I can deal with half cells if maybe I should barycentrically subdivide this thing and do it. Actually, Gunnells and I, some years ago, wrote a paper where we tried to do this by barycentric subdivisions on simplicial complexes. And it worked, but computationally, you got factorials coming into your computation everywhere. So this is not the way we want to do it, okay? And I'm going to describe two ways of getting around the difficulty. The first is a more algebraic way called Charbly's, okay? The name Charbly was coined because it comes from a paper by Ronnie Lee and Sharba from about 1976. The term is due to Lee Rudolph. Lee Rudolph's the only mathematician I know who also published poetry in the New Yorker. So there you go. Okay, so what's a Charbly? So basically, a Charbly is a certain kind of rectangular matrix. So for any non-negative integer k, consider n by n plus k matrices. I'm doing this over Q at the moment, so matrices with rational entries. And we'll have formal symbols. A is such a matrix. We'll have formal symbols A in brackets. And we'll be taking formal z-linear combinations of these symbols. The symbols are called the Charblys. The symbols obey certain rules that are reminiscent of cell complexes. Permuting two columns multiplies the sign by -1. Multiplying a single column of A by a non-zero scalar doesn't change the symbol. You should actually think of the columns as lying in the projective space Pn-1 of Q. And finally, I'm not going into the details here, but if A has rank less than, we simply identify it with 0. We only want full rank. So it's a very natural complex algebraically. You can put the usual boundary operator on it where you omit, it's a rectangular matrix, so by turns omit the columns and take an alternating sum. And it's a complex, so it computes the homology of something. And what it computes the homology of is very interesting because, well, to remind you of the Steinberg module, let me first remind you what the Tietz building is. And just talking about Q here, in the Tietz building Tn, we consider the vector space Q to the n. We consider all its subspaces. The Tietz building is going to be a simplicial complex. A vertex of the Tietz building is a proper non-zero subspace of Q to the n. Now, subspaces of Q to the n can form flags, and whenever the subspaces form flags, you connect the vertices of your complex into a simplex. So the Tietz building is the simplicial complex corresponding to flags. And it is known that this is homotopic to a bouquet of spheres, which would be the sphere of dimension n-2. Excuse me, a bouquet of many such spheres, only many. So the Steinberg module is the reduced homology of those spheres in the only dimension that matters, n-2. Now, by Borel-Serre duality, the duality of the Borel-Serre compactification, and let's say gamma is torsion-free, then the Steinberg module is the dualizing module in that case, going back and forth between homology and cohomology. So the Steinberg homology of gamma is, you say the homology of gamma with coefficients in your module tensored with the Steinberg module.
What is M?
M is any coefficient module that we're considering for gamma. Okay. Excuse me? Right. On this slide, I guess I'm just working over Q. Yeah. Now, the reason Lee and Sharba introduced the Charblys is that the Charblys are a resolution of the Steinberg module. So it's always an exact sequence of GLNQ modules, and if gamma is torsion-free, it's a free resolution, a gamma-free resolution of the Steinberg module. So that means it's one way to compute this stuff. So the Charbly homology of gamma is you tensor the entire Charbly complex with the module M that you're interested in, and then take homology. Okay, so at this point, we've got lots of homology theories flying around. And yes, the good news is if gamma is torsion-free, they're all the same. So the group cohomology, the cohomology of your manifold locally symmetric space x mod gamma with coefficients, in the local system coming from M, they're all the same. If you go to the Borel-Serre rectification, it's the same. If you do the well-rounded retraction back to W, the cohomology is the same. And that Steinberg homology and the Charbley homology are the same. No, the duality, the Borel-Serre duality says when I speak of Steinberg and Charbley, I drop to homology. And now, in fact, they're also the same if, again, that your module was defined over a field, say a finite field of characteristic P, and P doesn't divide the order of any of the torsion in gamma. So then it took Ash and Gunnells and I, we did want to think about what happens when the P does divide the torsion in gamma. So for SL4, the torsion in gamma is 2, 3, and 5, and it took 2 papers to sort that out. The first paper was about not 2, and the last paper was about 2. And so the results are in the cases that we care about in the slides that I'm going to describe in the future, they're still all the same, although it took work. So I put precise statements in Appendix 2, but I think I'll just move on here. Okay. Let's see. So, okay. So the Charbleys are a big abstract object, just all, essentially, except for the rank condition, essentially all matrices of rational entries. So that's, and if you're going mod GLNZ, that's not finitely generated. So this is, you don't just want to compute with them on a computer directly. So how does it relate to the well-rounded retract that I can compute with? Well, the well-rounded retract, I said the cells were characterized by their minimal vectors. So it's natural to take the minimal vectors of a cell, put them into a Charbley, to stack them up into a rectangular matrix. That's natural to try that anyway. So, so cochains for W in this way map into the Charbley complex. And so we could speak of the well-rounded Charbley subcomplex. Now, it doesn't entirely work it works for n equals 2 and 3. Again, speaking about SL and Q at the moment. It works for n equals 2 and 3. The reason is that if you know the Voronoi theory, all the Voronoi cones for n equals 2 and 3 are simplicial, or the largest Voronoi cone is in 6 dimensions before you mod out by homotheties, and it's a simplex of dimension 6. And the largest perfect form in n equals 3 is A3, which has 6 plus minus pairs of minimal vectors. So basically the numbers work out, and that the numbers of vectors characterizing a cell go into exactly the right dimension of the Charbley complex you want them to go to, 6 and 6. For n equals 4, there are 2 kinds of perfect forms. N equals 4 is, you're talking about a 10-dimensional space where these things live before homotheties. There are 2 kinds of perfect forms. There's the A4 lattice, which has 10 pairs of minimal vectors up to plus or minus. But then the D4 lattice, also known as Ray's configuration, has 12 pairs of minimal vectors up to plus or minus. So if you try to put the well-rounded cells into the Charbley complex, there's a cell with 12 columns that you want to put into the slot where 10 columns should go. And so it doesn't work. So there's ways to try to get around that by taking, again, subdivisions which Voronoi considered of that cell. But fortunately, we didn't need to, because we were computing in the cuspidal range, which is like H upper 5, which is, in this case, Charbley lower 1. So, and the difficulty I just described is way up at the Charbleys of degree 6. So we only needed the bottom of the Charbley complex. So the problem didn't affect us. Okay, well, so to summarize a bit, so Hecke correspondences act on the Charbley complex. Again, if you've got rational matrices with no condition on them but rank n, act on them by those, by the correspondence I described. You're still going to have a bunch of rectangular matrices of rank n. So Hecke correspondences certainly act. The Hecke correspondences do not carry W to W. So for that reason, we used Charbly homology rather than like any kind of cohomology of the space itself to do our computations. Again, to repeat, these in characters of 0 and in any characters bigger than 5, these cohomologies are all the same, and please see Appendix 2 for the remaining 3 cases. Okay, but now I haven't said what you actually do to compute these Hecke operators. So first, let's talk about H in the VCD. In other words, cohomology of the locally symmetric space in the maximal possible degree that will carry cohomology. For I know it's hard to chase through all the sizes of things. This is the best for Charbly's because in the VCD, that corresponds to 0 Charbly's, which is square matrices, not rectangular. So we just computed with square matrices. For n equals 2 and 3, that's within the cuspidal range. So a lot of the papers considered it for that reason. Another advantage is for n less than or equal to 4, all the well-rounded 0 Charbly's, all the well-rounded square matrices will have determinant plus or minus 1. That's not going to be true starting at n equals 5. Voronoi knew that some of those, he wouldn't have said Charbly's, but that the minimal Voronoi cones already start to have either determinant 1 or 2 at n equals 5, and then more beyond that. But one would have to deal with that in n equals 5. But not today. Okay. Anyway, Hecke correspondences carry these square matrices of determinant 1 to square matrices of determinant not 1. For instance, T2, 1 would carry them to matrices of determinant 2. Ash and Lee Rudolph, I mentioned in 1979, they developed an algorithm to replace these square Charbly's with a given square Charbly with a formal sum of some other square Charbly's. This replacement is a homology in Charbly homology, so you're not changing the homology class. And the value of it is, they figured out how to do it so that when you replace it, the determinant of A is going down, or at least you do it enough times and the determinants are all going to go down to 1. They can prove that. It's a recursive process. And it is a direct generalization of modular symbols, and many of you will be familiar with modular symbols for SL2 due to a number of authors. For a leading paper by Monin in the 70s about this. And modular symbols, as you may know, generalize continued fractions. So in fact, Ash-Rudolph is, in that sense, generalizing continued fractions. All right, so that's, using Ash-Rudolph, you could compute Hecke operators in the, at the VCD. Well, what about 1 degree below that? And we were interested in that because for SL4, the top degree was H6, but the cuspidal range is H5 and H4. And there's a duality relating H4 and H5, so we wanted to work with H5, but Ash-Rudolph can't do that. So here Paul Gunnells introduced a Hecke operator algorithm for H5. So that's 4 by 5 matrices, 1 away from square. Basically, for if you like enumerate all the well-rounded retract cells for SL4, well, there are 18 cells in all, but in this dimension there are only 3 cells, which the minimal vectors look like this. All the 4 by 4 subdeterminants in these matrices are 0 or 1. So if you can get an algorithm that shrinks determinants or subdeterminants, you'll be done if they're all 0 or 1. So Gunnells performed a detailed study of these 4 by 5 matrices and their subdeterminants. Geometrically, he's taking walls and building roofs over walls inside the appropriate complex. And he uses Lenstra-Lovash on sublattices to make the determinants smaller. So interestingly, his algorithm has never been proved to converge to determinants 0, 1, but we've been using it for 20 years and it's never failed, so that's great. Okay. Let's see. So, okay, so that's the VCD, the like top degree, and 1 away from the top degree. But of course, one wants to do all degrees if you can. So years ago, Bob MacPherson and I had some ideas for that, and we, after a long delay, we came back to them, and around 2016, 2017, saw how to actually prove it. So let me, in the next few slides, I'll describe this. We call it the Welltempered Retract. Okay, So let boldface G be the restriction of scalars of GLN for any number field n and any n. But we have working code when the number field is Q and for SL2Z and SL3Z. It's, I know personally when I am proposing an algorithm or thinking I have an algorithm for something, I get very nervous that, oh, like it could fail and there's 100 different places where it could fail. So I feel much better if I have the thing completely programmed out, at least for some non-trivial examples. And so at this point for SL3Z and some non-trivial examples like gamma naught of 11, I can, this algorithm that I'm about to describe is working. It's not fast, but it's working and it can reproduce the known results. So that's good. So in this exposition, I'll restrict to those cases. Okay, so here's, I'll describe the well-tempered retract. Okay, again, fix a lattice capital L, and we're, we have to do Hecke correspondences in the sense of L and sublattices M. So fix one of the sublattices M so that L mod M is Z mod the prime LZ to the kth power. Okay, so here's the idea. We're going to pick a real parameter, t greater than or equal to 1, and it's bounded above by the prime L. So t is a real parameter going back and forth, which we call the temperament. And we make a definition of any vector y in L, its tempered length is, well, if y lies in the chosen sublattice M, then the length of y is its length. But if the lattice, or if the vector y doesn't lie in the chosen sublattice M, then the length of y is deemed to be t times longer than it really is. So, okay, so you see, if you're in a good mood, then you think about, well, the Welltempered and Johann Sebastian Bach, and I'm going to play some preludes, and it's all, yeah. If you're in a bad mood, you're going to say, well, if a vector doesn't lie in my sublattice M, then I'm going to tell lies about it. I'm going to say that's longer than it really is. And the reason is I'm trying to do well-rounded retractions. Well-rounded retractions stop when a certain vector hits, like, the minimal sphere, say radius 1. If I'm telling lies about a bunch of vectors so that they're way longer than they really are, then according to my lies, they'll never hit the minimal sphere. So I don't have to worry about them. So to be more precise, for each t between 1 and L, I know it's a continuous family, but imagine you fix each t, fix it and do well-rounded retraction in the sense of lies, where, and you're going to get some result. It's going to be x will retract to some complex. As t varies, the complex you get will vary in a continuous way. So the slice at each, the complex as a whole for all t is called W tilde. W tilde is one dimension larger than W. It's W being perturbed in one more real dimension. Gamma acts by preserving the slices. Gamma doesn't change the t. Okay. The point again is that it's going to be a complex that continuously interpolates between its left-hand face and its right-hand face. Its left-hand face is W1. W1 means don't tell any lies, so the retraction just got you back to the old W I had before. When t is very large, in fact L is big enough, all you're doing is well-rounding M, because none of the other vectors are visible, they're all too long. So you're continuously interpolating between making L well-rounded and making the sublattice M well-rounded. And when you've made the sublattice M well-rounded, that's the M that occurs in the Hecke operator. And when you push down mod gamma, it becomes the multiple copies. Excuse me? Exactly, gamma does not preserve M, but that's, I wanted to not preserve M because that's how I get a correspondence. When I work mod the appropriate gamma, I'm going to get multiple M in all its translates, and those are my multiple copies. It's yeah. I've got a demo to show which might help. Okay, get out of this. Okay, this is going to be the well-rounded retract for SL2 and being turned into the well-tempered retract. Let's see, I want to go, where was full screen? Right. It's supposed to be an animated GIF. I don't know why it doesn't animate, but okay. That's a picture of the standard well-rounded retract in the Poincare disk model of the hyperbolic plane. And I'm going to vary t in some small discrete steps. So you see, in the Poincare disk model, I spoke about the matrix 2, 0, 0, 1 that took the central arc up. Here it's taking it to the right, keeping it straight because it's a different model. You see how the others vary. So now, notice up here, you've got like two y's that are coming together. And what we're going to see is they're going to come together as an x and then separate out as two y's in the other direction. They come in left and right, and they go out vertically up and down. Let's see. They come together, and they separate out up and down. What's really happening there is, if you know the Voronoi cone picture, the Voronoi cones are defined by a Voronoi polyhedron, which is a big convex hull of like rank 1 quadratic forms coming from your minimal vectors. When I tell my lies, I'm moving those points around. There's really a big linear programming problem here forming a Voronoi polyhedron. And what you're seeing there is dualized is planes crossing like this, you know, 4 planes that cross sort of generically, and they're folding out. They fold out to a place where they all cross at a perfect cross, and then they fold out 2 different ways. Okay, it goes like that. I guess I have time to show you one more picture for T3. You get, it's even cuter because you get, was full screen was F. Yeah. I'm going to increase my T gradually. Focus on this point here. You see how it's like a letter Y? It's like a letter Y, and on each of the arms of the Y, 2 more things are coming out. So that's, so 6 edges are about to converge on that point, and there they've converged. And when I keep going, they're going to diverge the other way, so it's going to be a Y in the opposite sense with 2 things coming out. And we're sort of small here, but you can gradually see it happening. Yeah. So, right, so I have a picture where the original well-rounded retract is here. We flow across in one more real dimension doing these changes you see here, and it ends with the sort of the well-rounded retract slid over to the side, as you see there. Okay, well, so now what do we do with this? Where did I have my talk? Yeah. Where's full screen? Yeah. All right, you see, the virtue of this is I've got this thing I've constructed is a cell complex because, well, geometrically, as you see, it starts as a cell complex. The cells flow across, changing their shape. They go through various bifurcations, but it remains a cell complex. So the Hecke operator is computed by, this map here is mapped down on the left face, and this map here is mapped down on the right face with a multiplication by t. Okay. Well, now if I claim that this whole thing is a cell complex, I haven't proved that at all. So let me just say a bit about how that is proved. So, you know, when we dualize the well-rounded retract and work with Voronoi cones, we're really working in X, viewing it as the space of positive definite matrices, Xij, say modulo homothetes. That's, of course, an open set in a space of this dimension, that is before the homothetes. So I call those X's linear coordinates on the space of quadratic forms. And so the fact is, if you just check through what I did with those, telling those lies and like using like norm squareds, a bounded subset of this W tilde can be computed as a big linear programming problem in the variables xij, and if you write it down, you find it's all linear if you just introduce a new variable u equals 1 over t squared. So the entire thing I described is just defined by a bunch of linear equations and inequalities. So you can, you write this down and well, I feed it to a linear programming solver such as, well, Sage's class polyhedron, which is wrapped around the professional quality solver known as PPL when you're working over Q. And so I don't propose this as the world's fastest algorithm. For each n, l, and k, you've got to solve a different linear programming problem. So you know, if I want to do SL3 and T21, I've got to solve a linear programming problem, which is in fact in dimension 7 because it's 6 plus 1. Then if I want to do SL3 T51, I've got to solve another linear programming problem in dimension 7. So, right, it is what it is. And it's still work in progress to choose the bounds large enough to get all the cells mod gamma. Well, let's see. I should finish up in just a few minutes by, so far I've described 2 techniques for computing Hecke operators, but I should end by describing some of our results. So I've alluded to Galois representations. Let me just remind you a bit about that. What goes on there? So now let F be a finite field of characteristic P, not QP, I'm just taking a p-adic Galois representation and modding it out down to a finite field. And let's say that this representation M I'm working with is actually now over the field F. Well, in the cohomology, I can consider eigenclasses for the Hecke operators, and let A, LK be the eigenvalue for T, LK. I'll be considering Galois representations of the absolute Galois group of Q into GLNF, which are semi-simple and continuous. We'll say that such a representation is attached to the cohomology class Z if, well, at least in the finite number of cases L where L doesn't, well, avoiding the cases where it divides either the P in the coefficients or the N in the level. The characteristic polynomial of the Frobenius is given by this. So that's the formula that one expects from classical theory of L functions and then from the theory of automorphic forms. So that's what this formula is what it means for rho to be attached to a Hecke eigenclass. We say that rho seems to be attached to a Hecke eigenclass if that formula holds for enough L that you feel confident about it. So what you compute as many Hecke operators for as many L as you can. You hope that the first few L determine a row that determine like row, like there could be at most one row that matches. And then you compute a few more L, and if it still matches, you say, wow, that's amazing, it matches. So, okay. So, so some of the results, well, yeah, I certainly don't have time to say all of this. So Avner Ash, starting from the 80s, and his collaborators have many papers on SL3. I think I'll skip those for the sake of time. But so with the time I have left, I'll focus on papers that Ash and Gunnells and I wrote for SL4, for the congruent subgroup gamma naught of n and SL4Z, working in the cuspidal range of cohomology H5 for various M. So we actually have a series of 7 papers now about this. And they differ in that which coefficients we use. So for a long time we used constant coefficients M. So we were thinking we're using constant coefficients over C, but that involves floating point arithmetic, and floating point's inaccurate. So we have a proxy that the field of order 1, 2, 3, 7, 9 is C. This is because 1, 2, 3, 7, 9 is the 4th prime after 1, 2, 3, 4, 5. Okay. So over a period of years, we did all levels prime and composite up to level 56 and forced the prime levels out to 211, although we didn't compute Hecke operators all the way up to level 211. The largest sparse matrix I personally dealt with during this project was 1 million by 4 million sparse matrix of mod P entries. on a laptop, which I forget how big laptops' memories were in the early 2000s, but not great. So, and I did it on a laptop because a laptop is what I had at that time. So, okay. Okay, then we didn't want to just work over C. We wanted to look at torsion coefficients. So first we did the computations over Z as far as we could push them and inquired which P come up. Well, so I'm sure you know that there are many interesting torsion questions, especially nowadays, like work of Bergeron and Venkatesh and so on, studying the asymptotics of the torsion in cases where, for number theoretic reasons, you expect big asymptotics of torsion. So this is apparently not one of those cases, you know, SL4. We were, you know, so those folks could get like, for modest sized levels n, they can get primes like this long in their torsion, and we're getting primes like 11 and 17, and well, you know, 11's nice. Okay. Then in later projects, we bit the bullet and worked at the primes that divide the order of elements of gamma 3, 5, and 2. Okay, and in our most recent paper, which has been submitted last year, is instead of constant coefficients, we did twisted coefficients, still of degree 1, but we did all possible Nabin types for gamma naught of n. That means gamma naught of n, you have the bottom right entry mod n. You take all characters on that. So, you know, you pick a p so that pretty big, so like 4 digits or something. I mean, so you pretend that fp is the complex numbers. You have to choose your p so that the exponent of z mod nz star divides p minus 1. Because if you were doing Nabin types over the complexes, then the exponent of z mod nz star, that's the number of distinct roots of unities you need to get every complex character. So this divisibility condition means I can get all the characters over mod p. So we did all levels prime and composite up to 28, and we did all prime levels up to 41. This work took longer. For one thing, we made a decision in this latter paper that we were really going to prove the uniqueness of our seemingly attached Galois representation in all cases. So we took the Hecke operators much higher than we had in previous papers. Also, for each n, you got multiple different Nabin types, so there's more work. Let's see. We've always wanted to find I'm sorry, I'm going to say cuspidal. We've always wanted to say a cuspidal class for SL4Z. We haven't found one yet, and getting sad that we haven't found one, but up to the limits of what we could compute. Let me just jump to a last slide here, say some things we have found over the years. We have found a variety of, we mostly find Galois representations that can be described using classical cusp forms coming from like SL2 boundary components of the Borel-Serre. We found some that come from SL3. We've found some that come from holomorphic Ziegel-modular forms of weight 3 on GSP4. So we found some actual evidence, at least computational evidence of Langland's functoriality coming from GSP4. Excuse me, couldn't hear. I believe for us it was, I think that gamma was level 61 or 67, I'm afraid I don't remember which, and I think the Ziegel modular forms were of a comparable level, I mean prime, so yeah. Another thing interesting related to the questions of Gauss classes is that we look for places where Galois representations from cusp forms of weight 4 seem to lift into our cohomology. Classical cusp forms of weight 4, we want to see when they lift into our SL4 cohomology. They seem to lift only when, according to the data, they seem to lift only when we've got trivial coefficients and when the special value, the central special value of that L function vanishes. So again, it's a connection to those classes. And the Hodge-Tate numbers of the representations. So the Hodge-Tate number of the cyclotomic character to the ith power is I. The Hodge-Tate number of a classical cusp form of, so weight k is, the numbers are 0 and k minus 1. So these are the numbers that would appear in the theory of motives. And so we always, the fact that we see 0, 1, 2, 3 suggests that our classes are always coming from a motive, but yeah, this is just computational evidence. So. Okay. Well, certainly time for me to stop there. Any questions? Oh, thank you.
Okay, so please give me some time to bring the microphone to you when you have a question. So, any questions or remarks? Okay, nice, close by.
I have a very naive question about the Hecke algebra you introduced. Does it have something to do with the Hecke algebra that the people of quantum group are considering?
I'm sorry. Oh, well, I'll repeat the question. The Hecke algebra that who?
That the people of in quantum groups consider also something that the name Hecke algebra. I think that the definition is completely different, but maybe there is some kind of relation.
Right. So the question is whether the Hecke algebra I introduced is related to the Hecke algebra one sees in quantum groups. I mean, my intention. What I intended to introduce was just the most classical Hecke algebra, the one that Hecke himself might have introduced. So yeah, I didn't try to make a direct connection to the quantum groups, but of course there's some there. So, yeah.
Any further questions? Any further questions?
Have you done any tests in level or in degree 1 below, comparing timings or memory use with the Gunnells 1 below?
You mean, so have I done any tests of the, like the thing I have with MacPherson compared to the timing test of Gunnells' things? No, I've not done any timing tests. And yeah, with all this linear programming that has to go into the thing, and no, Gunnells is certainly going to be the faster at the present time, but I want to, yeah, the speeding up the thing with MacPherson is work in progress.
Thank you. Any further questions? Okay, now the mic works. But thank you very much. So let's thank the speaker again.
Thank you. Thank you.